Having stated that the practice of energy modeling can be considered as operational research, it is possible then to break down a model to its basic components according to the operational research theory. Such components are structural inputs, parameters, variables, and governing equations that relate variables and parameters. Structural inputs are those inputs that describe the logical and physical structure of the system we are modeling. We define the technologies that exist in the system in terms of supply technology that introduce energy to the system, conversion technologies that convert energy from one form or carrier to another, transmission technologies that move energy from one node to another, and consumption technologies that remove energy from the system. We define the locations of our energy model, meaning these geographical regions that we are able to distinguish in our model. If a transmission technology exists between two locations, energy can flow from one to the other. We define the resources of the system, defined as a source or sink of energy that can, or must, be used by a technology to introduce into or remove energy from the system. Finally, we define carriers, meaning different forms of energy that our model will be able to consider, for example, different kinds of fuels, electricity, heat, high-temperature steam, and even transport. The combination of this information in correct order constitutes the reference energy system that we are going to consider in the model. Parameters are numerical parts of the model that describe the reference energy system and the behavior of technology involved. They are exogenously provided and are fixed throughout the optimization process. They cannot change in order to reach the optimal value of the objective function, as they are socio-techno-economical characteristics of the system. Some notable examples are efficiency, investment cost of technology, specific emissions, the final energy demand, and constraints imposed as maximum emissions allowed. Finally, variables are the numerical parts of the model that can change during the optimization phase in order to find the optimal value of the objective function. The objective function is typically the net present cost of the system, operated to meet the given demand. In order to minimize this function, the optimization process identifies the optimal values of the decision variables. Most typical decision variables are two: new capacity installed, meaning how much of which technology should be installed, and energy produced by each technology, meaning how to use the installed power plants. All the other variables are defined intermediate variables, as their values change as a consequence of the decision variables, such as operational cost and investment costs. Parameters and variables are interconnected between each other by a set of governing equations, with the most important one being the energy balance of the system itself.